Welcome to my Linux Driver Workshop 2025. In this workshop I want to give you an introduction to Linux driver programming, and when this video is online on YouTube I'm currently giving this workshop on a Linux event in Chemnitz. So my plan for this workshop is to do it on multiple Linux events, so if you want to see on which Linux events I was last year, all you have to do is visit my webpage gnu-linux.rocks. And here you can see the four locations I gave my workshop last year. This year I also want to be on some more events, but we will see if I can make it. Okay, so the goal of this workshop is to give you an introduction to Linux driver programming. Therefore, we will write the driver for this custom PCB connected to my Raspberry Pi Zero. So on this PCB we have an RGB LED and a button connected over an I2C GPIO expander. So last year we took a look at the GPIO subsystem of the Linux kernel. This year we will take a look at the I2C subsystem. Okay, so let's jump to the next slide and let me tell you a little bit about me. So I work as an embedded software developer, and you as if you already know this, that I have an embedded Linux YouTube channel where I'm focusing on embedded programming and mostly Linux driver programming. Here is a link to my webpage, and on my webpage you can find links to my GitHub page, my Mastodon and my LinkedIn account. And one driver of mine made it actually into the mainline Linux kernel. So I wrote a driver for a USB GPIO chip, and this driver was accepted in the mainline Linux kernel, which is quite cool. Okay, so in case you want to support my work, here are some options how you can do it. So you can buy me a coffee on buymeacoffee.com/journalsforlinux. You can send me a tip over PayPal, or since a month or so you can also use super thanks on my YouTube videos. So yeah, these are options to support my work. Okay, but now let's jump to the agenda and what are the plans of this workshop. So first I want to start by giving you a small overview of the Linux kernel and its tasks. Of course, this topic alone could take a 1 hour talk, so I will really break it down to the most important things. The next thing I want to do is I want to show you how you can set up a Raspberry Pi for Linux kernel programming. Then we'll take a look at the I2C Bus and how to write a Linux driver for I2C or for an I2C device. Then we will need a Makefile to compile our kernel module, and we need to learn some shell commands to manage our built kernel module. Then I will show you how you can add an I2C device over the sysfs. And then after step 7, there will be the first exercise where you can actually build the Hello World I2C driver and test it. And then I want to show you how you can access the I2C bus, but before you can access it, you have to learn a little bit about the PCF8574 GPIO expander, which I'm using here on my PCB. Okay, so after point 9 we'll have the second exercise where you can implement a driver which actually accesses I2C devices. But the last thing which is missing is an interface to user space, so we will take a look at how to create entries in the sysfs. Okay, and I also have some backup slides in case there is some time left, so I can also show you how a real Hello World Linux kernel module looks like, and we will use one macro for our I2C driver, which is called module I2C driver, and here you can basically see how this or what this macro is basically doing. Okay, so much for my introduction. Now let's start with the workshop. Okay, so first we need to talk a little bit about some theory, what the Linux kernel is and what its tasks are. So the kernel of an operating system is a hardware abstraction layer. And this hardware abstraction layer offers a uniform interface, so an API called system calls. And this API is independent of the processor architecture. So it doesn't matter if you're on your x86 laptop or on a Raspberry Pi which runs an ARM-based system. the same system calls are available on both systems if you're running Linux on it. Then the tasks of the Linux kernel are memory management, process management, multitasking, load distribution. So this is all somehow related to starting tasks or processes. So if you're starting a process, the process needs time to be executed on the CPU. Then the process needs some memory to keep its data. And if you are running multiple processes at once, you need a scheduling mechanism. And this is all provided by the Linux kernel. And the next important thing is, the Linux kernel also offers the ability to access the hardware over drivers. And this last point is what we are looking at today. And your user space application now only have to use the system calls to interact with the kernel. So examples for system calls are the open, close, read, write function or I/O control. And the cool thing is, when using these functions, they don't need any knowledge about the hardware which is actually accessed over the drivers. And Linux itself is a modular monolithic kernel with loadable modules. So monolithic kernel means basically all drivers and all kernel functionality is compiled into one binary blob, which is executed. But the downside with this is, if you include all the drivers in one blob, the blob will become huge, because maybe you have an AMD GPU, you have an Intel GPU, and all the drivers needs to be in that blob. And then even if you don't use an Intel GPU, you need the drivers available somehow. But to make the kernel a little bit smaller, they introduced the concept of loadable modules. So now you only have a kernel which basically gives you the most important functionality, and then you probe which hardware you actually have, and then you're loading a kernel module. So for example, if you have an Intel GPU, on boot up it's detected you have an Intel GPU, and then the loadable kernel module for the Intel GPU is loaded into the kernel. So this mechanism keeps the kernel smaller. And here in our workshop, we will only focus on how to write loadable kernel modules, because of course you can do both. You can compile a driver directly into the kernel, or you can build the driver as a loadable kernel module, but we will only focus on the later thing. Okay, and here are two pictures to illustrate the tasks of the Linux kernel. So here on the left hand side you can see HTOP, a process manager for Linux. So you can see we have a single core CPU system, but nevertheless we have multiple processes running in parallel, and this is due to the scheduling functionality of the Linux kernel. And here on the right hand side you can see a hard drive and a USB stick. And from a user, if you want to save a file to one of these storages, from a user space perspective, you are just selecting a location in your root file system or in your file system. You click save, and the drivers are actually responsible for talking to the devices and using the SATA controller to access the hard drive, or to use the USB controller to talk with the USB device. But you, from a user point of perspective, you don't see any difference in saving a file to the hard drive or to the USB drive. Okay, so in our workshop we will use a Raspberry Pi to do our Linux kernel programming on it. And in order to set up a Raspberry Pi for Linux kernel module programming, you need to perform the following tasks. So first, I would recommend you to update your package repositories and then run an upgrade on your system. So update all the packages on your system. Then the next step is to install the so-called Linux kernel headers. So the kernel headers are a subset of the Linux kernel sources. But the kernel headers only include the header files and the make files, which are needed to build a loadable Linux kernel module. And on Raspberry Pi OS, you can install the kernel headers by the package Raspberry Pi kernel headers. And then you also need some build tools like the GNU C compiler or Make. And normally on Raspberry Pi OS they came pre-installed, but if not, you can install them by installing the package Build Essentials. And one important thing to mention here is if you're using the package Raspberry Pi kernel headers, it will install the latest version of the kernel headers. But if you're using an older kernel because you haven't updated your Raspberry Pi since some weeks and there was a new kernel release since then, the version of the kernel headers and your running kernel is not matching. And this is why I'm recommending you to also do an upgrade and also to restart your Raspberry Pi, because when restarting, you're loading the newly available kernel and then the kernel headers and the running kernel will match and you can build and run your own kernel modules on it. Okay, so the next thing, in this workshop we want to write the driver for the I2C Bus. So let's take a look what the I2C Bus is and how it works. So the I2C Bus is a simple two-wire bus. So you have two signals for the whole bus. You have a data signal, which is called SDA, and you have a clock signal called SCK. I2C supports multiple frequencies, so you can have 100 kilobits per second, 400 kilobits per second, or 1 megabits per second. And if you're building a hardware where you are connecting I2C devices, it's important to assemble pull-up resistors for both signals. Okay, so this is how an I2C bus looks like. On an I2C bus you need one device which is called the master or the controller, and this device initiates all the traffic on the I2C bus. And then you have so-called slave devices, and you can have up to, I think, 128 slave devices available on your bus. Okay, I think it's a little bit less. I think it's only 126 maybe. Yeah. And each slave device has a unique address. So here, for example, slave 1 has address number 1, slave 2 has address number 16, slave 3 has address number 4. And the master now needs to decide to which slave it wants to talk to. And let's say it wants to talk to slave 2, then it can perform an access on the bus with address 16. And the possible accesses for I2C are a read access or a write access. So the master can read from a slave with a specific address, or it can write to a slave with a specific address. And that's basically how the I2C bus works. So now let's take a look at our first Linux driver. So we want to write a driver for our I2C device. And here you have to do the following steps. So first, you have to name the compatible devices. So you have to list all the devices this driver is responsible for. Then you have to implement a probe and a remove function. So the probe function is called for every device compatible with your driver on the system. And the remove function is called when you're removing a device which is compatible with this driver from the system. And then in the last step, you need to bundle the compatible devices and the probe and the remove functions and some other driver data into a driver structure and register the driver on your Linux system. So these are basically the steps, and on the next 3 slides you can see the instructions, the C instructions for doing so. So the Linux kernel is programmed in C. Nowadays you can also implement kernel modules or kernel drivers in Rust, but we will focus on C here. So for an I2C device, you need to include the header linux/i2c.h. And the prefix Linux here tells you, okay, this is a Linux kernel header here. Then down here we are creating a list of all the compatible devices. And for I2C devices, we can use an array from the type struct I2C device ID. And I call it myIDs. So this array has 2 elements. The first one includes the name myDevice. So this driver will be compatible with a device called myDevice. And to indicate the end of the list, we need to add an empty entry here in this array. Okay, and this macro here, module device table, basically tells us, please add to the I2C devices the devices named in the myIDs array. It's also possible to add some to an individual device some driver data, then you would have a second argument here in the array, which would be a pointer to driver data. But for our simple device, we won't need it. Okay, so now we have declared the compatible devices. Now we have to implement a probe and a remove function. So the probe function is called when a compatible I2C device is added to the system, and the remove function is called for if an compatible device is deleted from the system. So you can see here the return value of the probe function is an integer, so it will return 0 on success and negative error code else. And we have two arguments in here. The first argument is from the type struct I2C client pointer, and this is a driver, or this is a pointer to our I2C device. And the second argument here is from the type construct I2C device ID pointer, and I've called it ID, and this is a pointer to the entry in this compatible devices list. So if you would have multiple compatible devices, you can tell which device you have from this pointer. Okay, and what are we doing here in the probe function? We are using a function called printk. And printk looks a lot like printf, which will print a line to standard out. The problem is, in a kernel modular driver, we don't have standard out available. All we have is the Linux kernel's log. And printk adds one line to the Linux kernel's log. So here we are writing hello from I2C slave with address, and here we are adding an address like we would do in printf, and here we are accessing the address field of our client pointer, which contains the address of the I2C device. Okay, and here in the remove function, we have only one argument, only a pointer to our I2C device, and here we are printing one more line to the kernel's log, which tells us bye-bye I2C. Cool. Good, now we have named our compatible devices. We have implemented our probe and our remove function. Now we have to bundle these information in one driver. And here you can see how this is done. So here we are creating an object from the type struct I2C driver. And this object has a field called probe, or a pointer called probe, and this we have to initialize with the probe function we want to use for this driver. Then we have to do the same for the remove function. Then we have to name the compatible devices with this ID table pointer, and within drivers we can set some more information like the name of the driver, which is my I2C driver in that case. And then we have created the driver, but we have to register it to the Linux kernel. And this can be done with the function module I2C driver, and here we have to pass in our driver's object. And this function basically creates us the entry and the exit points of our driver. If we have time, we can take a look what this macro is actually doing. If not, you can just go through the slides and read it for yourselves. Okay, so from a code point of view, we are done. But we need to add at least one more additional information to the driver to make it compilable. And this is we have to give the driver a license. And this is done with the macro module license. And here the used license is the GPL license. And the reason why we have to add this license here is because some Linux or GNU Linux distributions will not allow you to load non-free drivers. So if we would have a proprietary driver license in here, some Linux distributions would refuse the driver to load. And we can add some more metadata with module author. We can name the author of the module. With module description, we can give the driver a small description. I will show you how I can print out this information later when we take a look how to manage kernel modules from a shell. Okay, so now we have created the source code for our driver. Let's say we have saved it in a file called I2C hello.c. So now we need a Makefile to compile it. The whole Linux kernel can be built over Makefiles, and so we also have to create a Makefile for compiling this kernel module. So here is a Makefile to build our I2C drivers, and I see I forgot to translate this headline here to English, but never mind. I will do this later. So the first thing we are doing, we are adding I2C hello.o to the variable object-m. So in the Linux kernel, there are 3 important variables when you want to build a driver for the Linux kernel. The first one is called object-y, and all object files listed behind object-y are drivers which are directly built into the Linux kernel. Then we have object-m, and all object files named after this variable are built as kernel modules. And there is object-n, I think. These modules are not built at all. The source files are there, but they are not used for the kernel build. Okay, and so here we are telling us, please build a Linux kernel module out of I2C hello.o. And the compilation of I2C hello.c to I2C hello.o is done automatically with some rules defined in the kernel header Makefile. Then we are declaring 2 targets, an all target and a clean target. And in the all target, we are calling make. We are calling the Makefile in lib modules. Shell -r gives us the current Linux kernel version. And here we are going in the build folder, and we're calling the Makefile, which is in this folder. With the capital M variable, we are telling the Makefile in which folder it should look for kernel modules to build. And here we are using the target modules. And for cleaning the build files, we do something similar. So we are calling the same Makefile again with the same folder for kernel modules, but now we're using the clean target instead of the modules target. So here I am connected to my Raspberry Pi, and let me show you the folder which we are calling. So this should be the folder, and here in this folder you can see we have some folders and files in here, and this one is important because that's the Makefile which is used to build our kernel module. And here it includes, we have all the include files we need for building the Linux kernel. Yes, so that's basically all which is here in this folder. And I told you the Linux kernel headers are a subset of the Linux kernel sources. So here on my local system, I should have a Linux kernel lying around somewhere. And you can see here we have much more different files and folders available. So these are the complete Linux kernel sources. This is just the Linux kernel headers, which just include everything needed for building a kernel module. Okay, so after the compilation, we have a file named I2C hello.ko. KO stands for kernel object, and this is our kernel module which we can load into the kernel. But how can we achieve this? Well, here are some shell commands for managing kernel modules. So with lsmod, we can list all the modules which are loaded into the kernel. With dmessage, we can show the kernel's log. And here, for example, we can check if the print made it to the kernel's log or not. Then we have the insmod, so insert module command, which loads the module we have specified here as a first argument into the kernel. With remove module or rmmod, we can remove a module from the kernel. With modprop, we can load a module into the kernel with all its dependencies, but the downside is modprop only works for kernel modules which are in a specific directory, so we can't use it for our modules right now. And I told you about the metadata we're passing to our kernel module, so the module license, author, and description. If we want to see these information, we can use the modinfo command and pass in our kernel object, and then we will see all this metadata here. Okay, so the last thing which we need to talk about is how to add an I2C device over the sys file system. So basically, therefore, we can change into the I2C folder, and then we are writing the compatible string and the I2C address to the file new device. And if you're doing this, the probe function of the driver compatible with this string will be invoked. So here I made a typo actually, because here I named it my under device. So this would not work. Here there would be an error that no module could be found. But if I would write my under dev and this address, our probe function should be called. And in order to remove an I2C address from the Linux system, we just have to write the I2C address to delete devices. And those two files are located in sysbus, I2C, devices, I2C, and the number of the bus. I will show you later how you can find out which I2C bus you have to use. Okay, so much for the first theory part. Now let's jump to our first exercise. Okay, so then let's do our first exercise. So here's the exercise. We should implement the Hello World I2C driver on a Raspberry Pi. The compatible device should be named RGB board. Then we have to build the module with a Makefile. We have to load the kernel module and check if the module is loaded to the kernel by taking a look at lsmod. Then we can add an I2C device over sysfs, and we can check the kernel's log and see if the printcap from the probe function is there. And then, last but not least, we have to delete the device and remove the module from the kernel. So let's go. I will create a new folder I will call RGB board, and I will jump right into this folder. Then maybe let's start implementing a Makefile because it's a little bit easier than the kernel module. So to the variable object-m, which contains all object files to be built as kernel modules, I will add I2C hello.o, and the .c file will be compiled to an .o file automatically over the kernel headers Makefile. Then I'm defining the first target all, and here I'm calling the Makefile in lib modules shell uname -r, which will give us the version of our current kernel, and then build. Then I will set the variable m to my current path, and that's where the Makefile should look for compatible kernel modules. And the target here is modules, because I want to build a kernel module. And the clean target is basically the same. The only difference is here I'm calling the clean target instead of the modules target. Cool, so much for the Makefile. Now let's implement the Linux driver. So I2C hello.c. First I need to include the header linux /I2C.h, and in here are all the necessary defines or structures are defined, the I2C driver is defined, everything is in here. Then next step is I have to name the compatible devices. I think the structure is called I2C device ID, but let's take a look at it. Yep, I2C device ID, and I'll call it my IDs. And of course this is an array. So the first element will be named RGB board, because that's the compatible string we should use, and the second one is just an empty element to indicate the end of the list. And with module table or module device table, we make the compatible devices known to the Linux system. So to the I2C subsystem, I'm adding the IDs from my IDs. Okay, then the next step is to implement a probe and a remove function. And the probe function I will call my remove. The first argument is a pointer from the type struct I2C client. I will call it client. The second one is a pointer, a constant pointer from the type I2C device ID, and this is pointing to the row here in this compatible table here. And what I will do here is I will call print k I2C hello, and I will print out the string hello says I2C device with address. And here I will print out the address, and in order to get the address I need to access the address field of this I2C client's struct. And then I will return 0 to indicate probing the device was successful. Then I need a remove function, which I will call myRemove. And the only argument here is from a pointer from the type struct I2C client. And let me copy these two lines here. And by says I2C device with address, and let's print out the address here. Okay, so now we have created a list of compatible devices. We have implemented a probe and a remove function. Oh, this should be my probe, not my remove. Sorry for that. And now we have to bundle this in a driver. So this should be called I2C driver, am I right? Yes, and I will call it my driver. So the probe function should be my probe. The remove function will be my remove. The list of compatible devices is my IDs. And let's set some driver data. Here I want to set a name to RGB board. Yep, and that should be it. Yeah, this semicolon here is too much. Okay, and now with module I2C driver, I'm registering the driver to the Linux kernel, and here I'm passing the object from the I2C driver object, my driver here. And then of course I need some module information like a license. This will be GPL because we want to write free and open source software. Then I will name an author. Here I will take my name. And something very common is that an email address is also passed in here in this square braces here. And let's also give it a small description. Hello world I2C driver. Yep. Okay. Cool, so that should be it. Let me try to compile it by running make. This will call our first target, which is all. So now it's building the module, and this will take a little bit of time. Okay, it's looking good. And the result here, so here are a bunch of build files, and the important one is I2C hello ko. If we take a look at it with file, we can see this is our, so this is basically an ELF 32-bit file, and this is our loadable Linux kernel module. Okay, so now the next step is we have to load this module to the kernel, but before, let me run modinfo to get some information about this kernel module. So here we can see the description, the author, the license, and down here we can see against which kernel version this module was compiled against. Okay, so now I will insert the module with the insert module command. So now it's inserted, and now if I'm running lsmod and search for I2C, you can see the I2C hello module is here. Okay, so now the next step is to add our compatible device. And therefore first we have to scan our I2C bus for devices. So with I2C -L we can see which I2C buses are available. And here we have just one bus sitting at I2C -2. So let's scan this bus with the -Y2 option. And we don't see any device here. That's odd. Have I connected it correctly? Oh no, please note. Let me check if I have enabled I2C here. Yes, I have to enable it. Now it's enabled. And now let's run I2C. Okay, now we have two I2C buses available. Yep. And if I take a look at I2C bus number 1, I can see one I2C device at address 38 hexadecimal. So this is the device which is connected to my Raspberry Pi. So yeah, this is this GPIO I2C converter here. Okay, so now let's add a device to the driver. Therefore, I will navigate to sys bus I2C devices I2C1. And here we have this new device folder and delete, no, not folder, file, and this delete device file. And to new device, I will write RGB board and the address, which is 38, new device. Okay, maybe I have to do this as root user, so let me try to run it again. Good, it worked. And now let's take a look at the last lines of the kernel's log. And here we can see our driver was loaded, and this message here, loading out of 3 module tains kernel, just means, okay, the kernel module you have loaded was not built together or was not shipped with the kernel which is installed here, and using this module is on your own risk, so you can break your whole system if you want to. And then here we can see the print from the probe function. So, and in order to remove the device, we just have to write 38 to delete device. And now if we take a look at the kernel's log again, we can see by says I2C device with address 38 hexadecimal. Okay, and now last we can do is we can remove the module. So let's remove I2C hello here. And now if we are taking a look at this again, we can see now the I2C device is gone. Okay, cool. Good, so much for the first exercise. I think now we complete all the tasks, and we can then take a look at how to access the I2C bus. Okay, so first let's talk about how we can use the PCF8574 IO expander. So basically, this expander offers you 1 byte you can write to or read from. And with the write accesses, you can set the outputs of the 8 available ports. So the PCF8574 offers you 8 GPIOs to write. And with a write access, you can set a value to the GPIOs. And with a read access, you can read out the value of the ports. And the values could be the one you have written before, or if you're using a port as an input, it will be the input. On my system, a button is connected to port 0. And a red LED of my RGB LED is connected to port 1, the green LED to port 2, the blue LED to port 3. And for the LEDs, if I set an output, so if I'm setting output P1 to 0, the red LED is on. If I'm setting P1 to 1, the LED is off now. So that's how to control the outputs. But how can we control the inputs? So you have to know, in this chip has very weak pull-ups. So for an input, we have to set the desired port, in this case P0 to a 1, and the button will pull the input to a ground level. And if a 1 is read from the port, the button is not pressed, but if we press the button, we will read a 0 from P0 because the pull-up is weak, and by directly connecting it to ground, this is much stronger, so we'll read a low level here. And here you can see how, so I2C uses last significant bit first. So if we want to access P0, we have to check out bit 0. If we want to access P1, we have to check out bit 1, and so on and so forth. Okay, so now let's take a look how we can access the I2C bus. And our gate to our I2C device is the myClient struct. So this struct I2C client is used to manage an I2C device in the kernel. So we have already seen the address of the I2C device is stored in this structure, and over this pointer we can also access the device, for example if we want to read from it, or if we want to write data to it. Okay, then in order to read the port we can use the function I2C smbus read byte. The only argument it takes is the pointer to our I2C device, and this will return the read byte on success or a negative error code else. And if we want to write to the I2C bus, we can use the function I2C smbus write byte. The first argument once again is a pointer to our I2C device, and the second argument is the value we want to write out. And this returns 0 on success and error code else. Okay, and this will lead us to our next exercise. Okay, here I've also forgot to translate it. Let me take a note so I don't forget to fix it. Okay. So let the RGB LED light with a color of your choice by writing to port 1 to port 3 of the I/O expander in the probe function. Turn off the LED in the remove function. Compile and test the kernel module, and an additional task is read in the value of the button at P0 in the probe function and print the value to the kernel's log. Okay, so let's do it. Good. So I will navigate back to I2C or RGB board, and I will open up I2C hello here. So here in the probe function I should now set the LED. And the way I'm doing this is I'm calling the function I2C smbus write byte. The first argument is the pointer to my I2C device, which is client in this case, and the second one is the value I want to write. And in order to light up an LED, I have to set the port to 0. So here I will set all the three LEDs, so the RGB LED should light, or should give us a white light, but maybe orange is more nice, so let's only set port 1 and port 2. Okay, and in case this returns something bigger than 0, an error occurred, and I will print out I2C hello, could not write to device, and I think in this case we could return a negative error code here, and this should be a new line character, of course. Okay, and now the next thing we want to do is we want to read in the value of the button. One thing to mention is here, so with this here we already have set port 0 to a 1. So the only thing which is left for us to do is we have to read it. So I will create a variable here, and I will call I2C smbus read byte. And I want to read from client. And in case value is smaller than 0, in this case an error occurred, and let me print these 3 lines here. So in this case I will print out could not read from device, and this should be a lowercase h. Yep. And in the remove function I have to turn off all LEDs, but here I won't do any error checking, because if it worked in the probe, why shouldn't it work in the remove function? Okay, and yep, that should be it. Good, so let me try to compile it one more time. So it seems we haven't made any errors while coding the module. Then I will load the module. Good, it's loaded, and now I will navigate to sys bus I2C devices I2C1. Then I will echo 38 or RGB board 38, and I will write it to new device. Good, it worked, and you can see here now, yep, the blue LED is on. Okay, the blue LED is on. That's a little, okay, yep, I know why, because I've actually made one error in the code. I will show you just in a second. And if I remove the device again, you can see the LED is turned off. And if we take a look at the kernel's log, you can see here, oh, I forgot to print out the state of the button as well. Sorry for that. Give me a second. Then I can also fix my second error. So in case print k I2C hello button is pressed. So in case value and 1 is bigger than 0, in this case I will print out is not pressed, and in case I'm reading back a 0, I will just print out a button is pressed. Okay, and the thing why this didn't work is because I have to do it this way here. So I'm clearing bit number or P1 and P2, and for the rest I'm writing a 1. So before I just said P3 to 1 and all the other stuff was written to 0. Yep. So this should hopefully work. So let me try to compile it one more time. Okay. I forget the comma here. Sorry for that. Okay. Now it should work. Yep, now it's looking good. So let's load our module again. Oh, or let's first remove the module. Then let's load it again, and let's insert our device, and maybe let's even press the button here. Okay, loaded. And now you can see it's showing us, or we can see a yellowish color. Okay, I think on the camera it's a little bit hard to tell. Then let's remove the device, remove the kernel's module, and let's take a look at the kernel's log. Okay, and here we can see the button is pressed. Okay, cool. So this worked. Cool. But one thing which is a little bit sad is currently we can only control the device in the probe and in the remove function. But in between, for example, we cannot read out the state of the button, and we cannot read out or set the value for the RGB LED. And this is a little bit sad. So it would be cool if you would have an interface to communicate with the driver while the driver is loaded. So in the last slides, we will take a look at one interface which is capable of doing exactly this. So we will talk about the creation of sysfs entries. So the sysfs is a virtual file system. We are already using it to add and remove devices from the I2C bus. It's used for the presentation and management of so-called kernel objects, K-objects. And these kernel objects enables interaction to the driver from user space. A kernel object is a folder in sysfs, and a kernel object offers attributes which are present as files over which we can communicate with the driver from user space. And the procedure is we have to implement the show and store function. So this show function is used to read an attribute. The store function is used to write an attribute. And then we have to add the attribute and combining it with the functions it should support. Then we have to create a kernel object and combine a sysfs file with the attribute. So these are the steps we have to do. And now let's take a look how these steps are done. So first we need a new header. We need the header linux/kernelobject.h. And up here you can see how a show callback function looks like. So the first argument here is the kernel object to which the store function belongs. Then we have the attributes of the kernel object, which are not so important for us here. But for example, over the attributes, you could see if the file is readable and or writable. And this buffer is basically where we have to store the data which are read out of the attribute of the kernel object. What I'm doing here is I'm calling the function sysprintf. And here I'm writing hello world and a new line character inside this buffer here. Okay, so if I'm reading from this kernel object or from this attribute, I will read hello world. And here we can see the store callback function. So the first two arguments are the same. The buffer is now a const string because it's written down to the kernel driver. And we have also a variable telling us the size of the buffer. And here I'm just printing out this buffer to the kernel's log, and I'm returning the amounts of bytes we have written. Okay, and up here I'm just returning the size of the string here, which is the return value of sysprintf. Okay, and down here I'm declaring the kernel object attribute, so I'm calling it myDev attribute. And here I'm saying this macro will create this attribute for us. The name should be my attribute. Then these here are the access permissions. So the first one is the owner of the file can read and write it. A member of the same group as the owner can read and write it, and all other users can access it. And this here is the show function. This is the show callback, and myDev store is the store callback. Okay, so we have created the callback functions. We have created the kernel object. Now we have to bundle it into a sysfs file, and this can be done with the function. So first we are creating the kernel object with the function kernel object create and add. So we are adding here my kernel object with and this here is a pointer again to our object from the type struct kernel object. So in case we are getting a null pointer here, the creation of the kernel object failed, and I will return the error code error no memory, because if we can't create a kernel object, we are out of memory. And down here we are creating a sysfs file, and here we are saying, okay, please use the kernel object my kernel object and use the attributes stored in myDev attribute attributes. And in case this returns something not equal to 0, also an error occurred while creating this file here. Okay, cool. So much for the theory. Now let's go to our last exercise. Oh, and I forgot to mention, of course, to delete the kernel object and the attribute, we can use these functions here. Sysfs remove file will remove the sysfs folder, and kernel object put will remove the kernel module. Okay, but now we can jump right to the exercise. Okay, so we have to add the folder RGB LED in the sysfs over the kernel module. We have to create the file LED inside the folder RGB LED. We have to implement the store function for this attribute to be able to control the three LEDs. By writing the string 011, the red LED is turned off, the green and the blue on. And an additional task, we can add a file button to the folder RGB LED, and we need to implement a show function for this file so that we can read out the state of the button over this file. Okay, so let's try to implement this. Okay, so the first thing we need are some global variables for our. So we need a global variable for our kernel object. So struct kernel object, and I will call this RGB. So this will be the file for our, or the kernel object for controlling the RGB LED, and I need a second one I will call button. Over this we can read out the value of the button. Good, now we have to implement the show and a store function for the individual files, and maybe let's start with the store function. So static ssize t or ssize t, and I will call it RGB store struct kobject, then struct kobject attribute, then const char buffer, and size t count for the amount of bytes which we want to write. Okay, so in case count is smaller than 3, I will return -1 an error, because here I need at least 3 chars to show this string here. And in case of success, I will return count. Okay. And now we have, and one thing I also need, one global variable, is from the type struct I2C client I2C def. So I'm using, because I don't have this available here to have it available in my callback functions, I will set I2C device to client. So I have this pointer available in the store function here. Okay. Then here I will declare an unsigned 8-bit variable I will call val. And then in case, so at first I will set val to all ones, so all LEDs would be turned off. And in case buffer 0 is equal to 1, in this case I will clear port 1. And then I will do the same for the second char and for the third char in this array. And at the end I will use I2C sm bus write byte. Write byte. So I will write to my I2C device and I will write out the value here. Okay, so this should be the store callback. Now let's create the attribute. So static struct kobject attribute, static struct kobject attribute. I will call it RGB attribute, and this is equal to under attribute RGB. This should be the name. Then the permissions, I will use the same permissions here. So I don't have a show callback, so I will set this to null, and then here I will use RGB store. Yep. Okay, and now I need something similar for the button. So maybe let me copy this here. And I will call it button show. So this isn't a const char here, or a constant string anymore. And here I will copy this line here. And here I will just return as printf, and then I will add the line. Okay, and here I will print out button is pressed or not. But before doing so, I of course have to read the value here of my button. So U8, and then I can pass it in. Instead of client, I want to read from I2C device here. Yep, and that should be it. Now I can create the attribute. I will call it button attribute. So the name should be button here. The permissions are the same. Now I only have a store or show function, which is button show, and the store function I will set to 0. Okay, so now the last thing which is left for us is we have to add our kernel objects here in the probe function. And this I will delete. Yep. Because then we can read out the state of the button from our sysfs entries. Okay, so let me take a look how to do it. Okay, we need the function kobject create and add. Oh, I think one kobject would be actually enough. So RGB board, okay. So RGB board is equal to sysfs kobject create and add. And I want to call it RGB board, or RGB LED should be the name. Sorry for that. Board, and in case this returns 0, I will print I2C hello cannot create kobject, and I will return error no memory. Okay, and then I need to add my attributes. So sysfs create file, and then the status variable here. Sysfs add file, or create file. So the first argument is the kernel object for which I want to create this file, and the second one is the attribute, which is RGB attribute dot attribute, and Then of course I have to check if status is bigger than 0, because if so, I will print out cannot create sys RGB board RGB or RGB LED, sorry. Okay, and I will return the status code here. And one important thing is, of course, in the case of error, I have to delete my kernel object, and this can be done with kobject put. Okay, and then let's do the same for the button. And in case here I also have to remove my sysfs file. And here I have to paste in my kernel object, which is RGB board, and the attribute, which is this one here. Okay, and let me copy these two lines here, because in the remove function I also have to clear the sysfs entries and the kernel object. Okay, and I think I forgot to add the header. So the header was called kobject.h. Okay, so let me try to compile it, but I think here maybe I made some mistakes. Let's see. Yep, and I think I know the first one already. But we'll see. So, kobject put. So the first error I did is here I have to specify to where I want to write it. So of course I want to write the string to the buffer. So that's the first error. And then let's take a look at the second one. It doesn't know kobject put. Did I misspell it? Yeah, kobject put, I just misspelled it. Object put. Okay, let's try to compile it one more time. Because I'm using this in multiple locations. So of course here I also have to use it, and here also. Okay, at least it compiled. Good, then let's insert our kernel module. This worked. Then let's jump back here and let's add our device. Okay, then let's take a look at sys RGB LED. Yes, and in here we have two files. So let's cat sys RGB LED button. Good, permissions denied. Button is not pressed. Now let's press the button. Sorry, I won't give you the camera right now. So I'm pressing the button. Sorry. Now I'm doing it again and I'm getting button is pressed. So the store function is already working. Now let's try to write to sys RGB LED RGB, and of course here I have to pipe it to sudo t to get it working. Okay, now it's blue. Now it should be red. Yes. Now it should be green. Yes. So this is also working pretty fine. Now it should be white. Yep. Let's call it white. Okay, cool. So this is working. And now if we remove our device, delete device. Okay, the LED is off now, and if we take a look at sysRGB, so there is no RGB board device left. Cool. So yeah, this worked pretty well. And this was our last exercise. So yeah, that was my Linux Kernel Workshop 2025. I hope you've enjoyed it, and if you want to see this workshop in action, just follow me on Mastodon, because there I will post at which Linux events I have applied and which did accept me. So yeah, just take a look there to see at which locations I will give my Linux driver workshop. So yeah, I hope you've learned something and enjoyed the video. Thanks for watching, and goodbye.